welcome to the second day of DNS-OARC 33. And my name is Včelák. I'm on the program committee and I will be helping to run this session. So this morning we will have 4 presentations total, 2 and 2 with a short break in between. If you want to participate, please use the chat for general discussion. But if you want to ask questions and want them to be answered by the speaker, please use the Q&A feature in Zoom. You will find the Q&A button at the bottom in the window, in the Zoom at the bottom of the Zoom window. With that, I would like to introduce the first speaker. Our first speaker is Shannon Weyrick of NS1, and he will talk about pktvisor 3, summarizing traffic with sketch algorithms for observability and DDoS mitigation. So Shannon, if you're ready, please share your screen and go ahead.
Yes, hello everybody. Can you hear me?
Yeah.
Okay, very good. Hello, my name is Shannon Weyrick and I work at NS1, and I'm going to talk about our newly released tool called pktvisor. So jumping in, what is pktvisor? Pktvisor is a network visibility tool. This is sort of another tool to put in your observability tool stack. And its whole goal is to summarize traffic in real time directly at the edges. And it does that with these things called data sketches, which I'm going to talk about a little bit. And there's 2 different ways that it presents the summary information. So it includes a command line interface, and this lets you be directly on a node and in a terminal program and updating, watching the information in real time. And then it also exposes an HTTP API, and this is used for collecting the summary of information to a central location. And this is so you can get that global view of all the nodes that you're monitoring back into a central database and do graphing with something like Grafana, for example. Just to give a quick preview of what types of metrics we're talking about in terms of summarizing. So it's got layer 3 packet information, so a lot of packet counts and rates, breakdowns by protocols and so forth. Then it gets into deeper packet inspection. And so obviously we care a lot about DNS. And so we get into DNS counts and rates and breakdowns by protocol and response code there. But then we start to get into some of the more interesting ways we can summarize with the data sketches. So for example, cardinality is interesting to us. And this might be how many source or destination IP addresses have we seen inside of a time window, or how many unique DNS queue names have we seen inside of a time window. It can also do things like track DNS transactions, so watching query and reply pairs and getting timings out of it. And then one of the main ones also is heavy hitters or frequent items. And so we care a lot about what are the top 10 IPs that we've seen in the window, what are the top 10 ports, queue names, and so forth. So I'll go into more detail on some of these stats a little later in the talk. Just to give you a quick view of what the terminal program likes, just to throw you in and sort of whet your appetite. This is what it looks like. You can see a lot of information kind of crammed into one view. There's a lot of information going by in the header. That's a lot of counters and so forth. And then most of the real estate is taken up by these heavy hitters, these top 10 lists that I mentioned. And this is just the on-node view. This is the terminal view. I'll go through also the global view. So I wanted to set up a little motivation for where pktvisor came from. So the newest version that's out is V3. There was a V1, and that goes all the way back to 2014. And when NS1 was still a pretty new company, and we needed visibility across our global anycast network. So we are a managed DNS provider. We provide authoritative DNS. We have 26 POPs around the world in our main network that we operate. And the visibility is good for, of course, just nominal operations. What are our nominal traffic patterns? What's the seasonality look like, and so forth. And debugging is another useful thing if we're bringing up a new node or we have some problem with a particular node. And then finally, DDoS, right? Or really just understanding malicious traffic, right? Is this traffic spike we're seeing malicious or not? And if it is, what are the properties of that? So we can mitigate the attack. The original version is a fork of NetSniff-NG, which is an open source traffic analyzer. The first version we made was pretty much just bolting on DNS functionality to this tool. And it did provide this terminal DNS top-like functionality with some of the information that we talked about. It remains open source. You can find it on the NS1 page if you're interested. It was mostly used on node. We did set it up to do some central collection, but it did have, it wasn't the easiest to do, basically. It wasn't made for that, and trying to collect the information coming out of it was hard, all right? So that was one thing that we wanted to correct. You know, some of the other problems that we had with the original version, one of the gaping holes was that it just didn't support IPv6 and TCP. So obviously that was something we needed to correct. It didn't track the transactions as we're talking about, so it didn't match up query and reply pairs, and that was, we knew we were losing some information, and just resource usage in general was a bit of a challenge. So as we thought about rewriting this, there were a couple of guidelines that I wanted to adhere to. So the first is that we want to summarize data. This particular tool is about summarizing. It's not about collecting all packets. And so, as I say here, we're interested in a distilled signal, right? So not the raw stream. And we're interested in two views. We want to be able to understand real-time information that's directly on these nodes. And we also want to understand the global view, which we know is a bit lagged, right? Like it'll take a little time to get that information in, but we have that global view. And so these two different views of understanding this information were important. Secondly, sliding time window with a JSON interface. And this really comes down to just having, you know, a clear way to track the traffic over time and to expose it so that we can automate it against it easily. And then finally, fix the holes, right? So obviously IPv6 and TCP needed to be first class. Efficiency and getting new metrics in was a goal. So I'll dive into those a little bit deeper. So this solution was not meant to be for data warehousing, right? And so intentionally, it was not meant to be an audit log of all the packet information that's coming into the network all the time. There are other solutions for that, obviously, including, we're talking about some at this very conference, but this is about summarizing. And so the goal is to summarize with counters and with these data sketches directly on the edge. And so distill that signal at all the edges. And the good thing about this is that it reduces complexity, right? And so there's fewer data requirements. The data requirements are much lighter weight, and also it's a less complex distributed system, right? So in order to pull the information out and get it back into a central location, get it into a database, there's just fewer moving parts going on here. But that's at the expense of querying flexibility, of course, right? Where you're not able to ask this just arbitrary questions on the raw data. The questions you can ask it have to do with the things we're summarizing, of course. One really nice thing is that we can get fast dashboards out of this, right? Because the data requirements are so quick, it's really nice to pull up like a couple months worth of summary in a few seconds. And you know, in terms of the actual data rates we're talking about, so a single summary that we're exposing in JSON for a single node is something like 7 kilobytes of JSON uncompressed. And so if you imagine an edge network that had 100 hosts in it, you're only collecting something like 1 megabyte per minute, right? So like call it a gigabyte a day, and that's uncompressed. And another really nice property of this system is that that data rate is not a function of the traffic rates. It's a function of the number of hosts, right? So even if you had 0 traffic on your network, this would be your data rate. And on the other hand, if you had a giant DDoS or a bunch of spikes, it's also your data rate, right? So I think that's a nice property. So the information is exposed in this sliding time window. And the way we do it is to keep n individual minutes. And by default, we keep 5 minutes of information. And each one of these buckets includes all of the summary information. And the way it works is that we're able to expose 2 views. We're able to expose a merged view. So you can get the entire window where these buckets merge together and show like a 5-minute view, a 5-minute summary. And you can also pull an individual bucket from the API. And we use both of these things in the command line version when the terminal is following the traffic. What you want is, as an operator, you want to be watching, you know, what is this sliding 5-minute time window of summary real-time information. On the other hand, when you collect centrally, you're interested in collecting a single full minute at a time. And so that exposes the most recent full bucket, number 1 here in the graph. And it pulls that every minute on every node into that central database. And because we're just using HTTP to expose JSON, it's not opinionated at all on what kind of collector is used or what kind of central database is used. You can work it into your observability stack. So the last guiding principle here, plug the holes and make it better, right? So, so IPv6 and TCP are now fully supported in this version. With the original version, we had the problem where running, every time you ran v1, it would run a new analyzer, it would run a new sniffer, basically, right? And that takes a lot of resources. Now, since we're just running a single daemon per node, and it's exposing the information on HTTP, it's very efficient. You can have operators connect to the node, no problem. This version is tracking DNS transactions now, so it's watching for query and reply pairs, and it's getting information out of it. It can also work on a PCAP, so it doesn't just have to be live capture. It can be fed a PCAP if you've got a system that's capturing those and you would want to summarize them. You could automate that, and you could get the summary by running it on PCAPs. And then the sketches we keep talking about. So we get these new interesting metrics, cardinality and quantiles. And again, I'll get to that soon. And there's the concept of sample rate too. It turns out that you don't have to deeply, fully inspect every single packet to pull the summary information that we're interested in. And so we can save some resources by having a sample rate. The rate right now is currently manual, but this is something we're thinking about even making dynamic. And if it's not doing a desample, it'll still continue to update some of the summary information like the packet counts and the simple counters. So under the hood, what does it look like? So there are two binaries essentially that get built as part of this system. And the first is the capture daemon, right, or the agent. And this is written in C++. And then there's the terminal side of it. And this is a simple Golang program. It's using this ncurses-like library here, which is very good. And its job really is just to spin up that terminal program, connect to a local or remote daemon, get that summary information and expose it to you in this, top like 1 second updating refresh. And then we get to the two main libraries that sort of make PacketVisor go. So pcat++ is the capture library. It is an abstraction layer over packet capture and provides some other nice functionality like TCP reassembly. It is, we're focused on the libpcap backend, but it actually does expose other backends. So you can use it with pfring, you can use it with DPDK, which we haven't experimented with, but there's interesting possibilities there. So that's how we get the packets into the system, and then it's all about counting and summarizing, right? So Apache Data Sketches is an open source library that's out there that exposes these data structures. And that's what we use to do the summarizing. And I'll talk about that in the next slide. It's got optional maxmind support that'll give GeoIP and ASN information into those top-end tables. It's a pretty small and new code base. I tried to keep the dependencies light. So really the only library dependency is this pcat++. Everything else is header only. So it's super easy to build yourself if you like. And at NS1, we use a lot of containers, we use a lot of Docker, and so this is Docker first, if you will. It's available on Docker Hub. Super easy to pull that and run it and try it out if you've already got Docker installed. So in terms of performance, not something that's been a big focus in the 3x branch so far, but to talk about memory and CPU real quick. So when there's no load on it, it starts at something like 13 megs of resident RAM. On a fully loaded production window, you might expect this to go up to something like 200 megs of RAM. And how much memory it uses is a property of how you tune these data sketches. So that's actually tunable, but there's a known limit to that. In terms of packets it can capture, so it's been measured at better than 100,000 QPS on a single node in a single instance before it starts dropping some information from the buffer. Nothing goes wrong with this except that the summary starts to become inaccurate. And there's several ways we can think about optimizing this as we go forward. So the data sketches, again, rely on Apache data sketch library. And so what data sketches are, these are these fast and probabilistic data structures. And these are designed for streaming. You feed it big data essentially, and it summarizes for you in real time. And what probabilistic means is that all of the results that it's feeding wind up being approximate, right? So if you need a tool that's giving you exact counters, data sketches are not the right tool. But if you only need a summary, if you're okay with approximations, then they're excellent. And the approximations are within defined error bounds, right? So you can actually choose as you spin up your data structures how big you might want that error percentage. And right now, pktvisor kind of hard codes a good balance, hopefully. But they do provide to us, outside of the counters which come for free, we get cardinality, we get these heavy hitters, these frequent items, and we get the quantiles. And so the data sketches themselves are designed to be merged, and that's how we support the time window. And so when we have those 5-minute buckets, it's got 5 separate data sketch structures per, and then it merges them together so we can get that view. And this is a built-in functionality to the sketches. And an interesting piece of functionality we could get out of this is to think about merging, exposing this raw binary sketch data and merging that across not just, right now it's merging a single process. We could merge across nodes in a data center, or even merging across data centers itself. Okay, I'm going to get into showing off some of the things we're summarizing in a little more detail. So here's the command line UI. Again, it's visualizing all the summary stats in the time window, the sliding time window on a single node in real time, right? So this is the most up-to-date real-time information. And you can run this locally on the node, or because it's in the end just hitting an HTTP server, it can also connect remotely to the pktvisor daemon if you'd like. It's efficient for multiple operators to use the same one for the same reason. And it's updating once per second, right? So back to this view. I'm sorry about the sample data. I didn't have great sample data. This is actually just a capture from my local network, but it exposes most of the interesting information here. So if you look at the top, all of the packet information is highlighted. And so this is like your L3 data, basically. It's how many packets, what are the breakdown by some protocols. It does understand ingress and egress. And at the top right, we see deep samples, and that's the sampling functionality I talked about, where it's you can select how many times is it fully deeply inspecting the packet and filling all of the data sketches out. And that can be a lower percentage. And then we have packet rates. And so here we see packet rate in 37 per second. The 37 per second is an instantaneous rate. And what we see next to it is percentiles, right? So this is where it gets into the quantile sketches. And what we're seeing here is that in the time window, which is shown, it's actually in the next section down, but you see exactly what the time window is. In this time window, the P50 of the packets per second we saw was 0. On up to the P90, P95, P99. And so we get that information in a very quick glance for both ingress and egress. And then next to that, we have cardinality. And so this is super useful information. So we see that it answers the question, how many unique IPs have we seen in this time window for both ingress and egress? And it's kind of hard to see in this view, but when you do collect this as a time series, you can see it as a graph over time. And you can see seasonality, and you can see spikes when both non-malicious and malicious traffic comes in. And so the section below that gets into the DNS-specific stats. And so we see a similar breakdown in terms of how many DNS wire packets, UDP, TCP, so forth. Now we see query and response counts. And then transactions. So it is matching up those queries and responses, and it's tracking it differently from in and out, right? Where in would be we're running a server, a DNS server on our node, and clients are querying us, and out would be either the operating system is going out and making a call, or we're running a recursive resolver on our system that's going out and making a call. And we have timings on both of those. So now we're using quantiles here for the timing information. So what it's saying is that the P50 of all the incoming DNS queries is 20 milliseconds, right? And so on up to the P99 of 318 milliseconds. And again, this is all done in real time for the time window that we're seeing. And finally, on the right side, we see another cardinality. So this answers the question, how many unique queue names have we seen in this time window, right? And again, really interesting information if you have this as a time series, and you can see the seasonality, and you can see when spikes happen. And we compare that information, again, to look for attacks. I'll go into that for in a second. Below that, we just have counters for the ARCOs that are coming out. And again, here's the time window. So we're saying that as an operator, I'm seeing exactly the information that's been summarized from 643 to 647 here, and exactly how long the period is. And then finally, at the bottom, we see the heavy hitters, the top end, right? So right now we're storing, or the API exposes the top 10. I think the UI right now is showing the top 7 just to fit everything in. But we have, you know, a lot of interesting information that we care about is DNS operators, including DNS summary information, the queue names at different aggregation levels, the timings, the queue types, and so forth. There were no NXs or serve fails in this time period, but those would be listed in terms of counters for the top 10 that we saw, also for refused. There's some generic IP information and DNS port information, and then at the bottom, we see the maxmind information that I mentioned. And for the slow in and for the slow out, it's actually using the P90 of the timings that it's tracking to figure out which queue names it saw that were above the P90. And so any that were above, that were slower than the P90, show up in this top 10 list over here.
Shannon, this is the timekeeper. There's 5 minutes left in this presentation and 5 minutes of questions following.
Very good, thank you. Okay, centralized operations. So the way we do centralized operation is to collect that summary information with Telegraph, which is open source. There's a generic Telegraph HTTP input plugin that once a minute will pull a full metric bucket from all of our nodes. It uses RabbitMQ to get that information back to our core. And we're using Elasticsearch as our main central database. And there's, again, a generic plugin to get that information into the database. So it's a really simple setup. And you can, like I say, you can work this into whatever observability stack you happen to have on your own systems. And here's what the global view looks like. Like a lot of people here, I think we use Grafana to visualize a lot of things. And so this is one of the dashboards with some sample data in it. And so, you know, you see global packet rates. This is a mix of all the nodes across all the POPs. Aggregating together. A couple of these graphs are done such that they're symmetrical with the ingress in the positive and the egress at the negative. So it makes it easy to see, make sure that we're sending and receiving data properly. In particular, this is graphing the P95 in the main graph, and then the dots represent the P99. So we can see spikes that happened above and below that. We see similar for the packet rates for POPs and for query response pairs. Here we can see the nice seasonality of the POPs. Yeah, there's a DNS protocol breakdown. We can see, you know, what traffic is coming in across everything. And then global NX attack view. This is where we start to marry some of that interesting information. And so here we have cardinality of the IPs that are querying the system. We have cardinality of the queue names that are coming into the system. And then we have the rates of NX domain responses. And so probably most of you have recognized what we're going for here is that our random label attacks that are so possible, happen so often. This helps us spot that, right? For all those things, if it's a distributed attack, we will expect IP cardinality to spike. We will expect queue names cardinality to spike, and we will expect NX domain responses to spike. Just another view of some of the information. Here's the DNS transaction timing, so we can see the incoming and the outgoing timings graphed again with some dots showing P99s and P50s. And then here's another attack view where I just happened to call out where we saw a spike in source IP cardinality, but not a spike in queue name cardinality. And that means it wasn't a random label attack. In particular, this happened to be a TCP SYN attack. Okay, centralized top end. One thing I didn't show for global was the ability to show these top end tables across the entire network. So it turns out that this requires MapReduce job. And that's not supported in Grafana or Kibana, unfortunately, but it is supported in Elasticsearch. And so you can find on GitHub a script that'll do this for you. It calculates the global top end for the selected nodes, but unable to put it in the dashboard we want. So there's a separate dashboard that's in progress on GitHub to show this for now until Grafana and Kibana can support it. Okay, that's most of the summary. So this is an open source project. Of course, we welcome collaborators. Anybody who's interested in trying it out and giving us feedback and or helping develop, please contact us. There is some documentation for the API that's exposed. It's in progress, but it's available in open API format and on Swagger Hub here. And just quickly on some of the future plans and ideas. So a control plane is one idea. So being able to not just pull summary information from the API, but be able to write to it and set up dynamic policies and talk about exactly what we'd like to summarize in any particular time is one idea. Allowing other types of streams. And so it doesn't have to be a packet capture necessarily. We could be summarizing things from a message queue or a pipe. So we could consider that an abstraction. And also same with other protocols. So DNS, obviously, we're very interested in, but there are other protocols that it might make sense to have as modules that can summarize things. And maybe new ways to probe. So eBPF probes that are looking for application information is an idea that's come up to explore. And of course, optimization is always interesting, and being able to target a single node to support up to hundreds of thousands with a dynamic sampling rate is on the backlog. And that's about all I have. So thank you very much. I hope this was interesting, and I'd be happy to answer any questions if they have any.
Thank you, Shannon. That was a nice presentation. And at this moment, we have 3 questions in. So I will read them to you. So the first question is by Matthew Poundset. Is the command line UI screenshot you shared single host information, or is that summary data?
So it is a single host, but it's summarizing the time window. But it is a single host, yeah. So the command line interface will always be a single host. It could be local, it could be remote, and it's summarizing the time window as it shows here, for example, 643 to 647, but single host.
Okay, thank you. The next question is by Ralph Weber. Cool tool, thanks a lot. Would it make sense to split domains based on the public suffix list rather than just number of labels?
It absolutely could. That's one of the nice possibilities about pktvisors. It could make sense to do a lot of different types of summaries, right? And this is where you get into that line between having, collecting all the packets and being able to ask any questions later versus what we're summarizing is like, you have to pick things in the end that you want to summarize. What I'd like for it to be is a way to summarize a lot of different things in pktvisor, but have the ability to choose what you're summarizing, right? Like you don't need a summary of all the options, or not every use case means you need all the options. And so what I'd like to see is we support a lot of different ways to summarize different protocols and to different depths of things, and then have a control plane that can control what we're summarizing dynamically.
Okay, thank you. And the last question is by Tomáš Křížek. Is it possible to monitor DNS over TLS or DNS over HTTP queries as well? Any plans to support it? TL sessions keys could be locked temporarily and the traffic decrypted.
Yeah, so we're absolutely interested in that kind of support. It doesn't do that at the moment. So I'm interested in working with folks on the best way to do that, right? Like one way to do it would be to put pktvisor between some kind of termination and where it's sending to, so behind a proxy. That's the only way it could work right now. It doesn't understand the keys, it can't unencrypt. But if there was native support for that, I think that could be super interesting.
Okay, and as you were answering, we received yet another question from John Todd. Following on the last question, what would be lost if the collection model was converted to DNS-stat?
What would be lost if the collection model was converted to DNS-stat? I unfortunately don't know the answer to that because I'm not as familiar with DNS-stat.
Okay, so hopefully we'll be able to follow offline. And yet another question by Ray Bayliss. Where's the bottleneck in the capture process? Is it done similar captures at, I have done similar captures at 4.5 times your quoted rate.
Yeah, it has to do with the deep inspection, I think. How deeply are we inspecting all of the packets, and how many different, for example, sketch algorithms are we putting them into? Because remember, we're doing a lot of processing with these sketch algorithms in the end. And they're built to be fast, they're built to work with streaming, but they do take CPU, right? So I think it's a matter of how deeply you're analyzing. And that's why I think it's also important to provide some kind of control to select the type of analysis we're interested in, so we can balance that.
Okay, thank you. That's all the questions we got. Thank you, Shannon, again for your presentation.
Thank you.
And with that, we'll move to the next speaker. The next speaker is Robert Šefr, and the title of his presentation is Neural Networks and Challenges in Detection of Malicious DNS Traffic and DGA Malware. So Robert, if you are ready to share your slides.
Yes,
Awesome.
Sharing it right now. Okay, can you see it?
Yeah, I can see it, I can hear you. So the stage or virtual stage is yours.
Thank you. Okay, I would like to dive into what we are doing on our DNS resolvers. in regards of detection malicious traffic or infected hosts. So the presentation is about the machine learning we are doing to detect domain generation algorithm or algorithms, different ones, to detect sequences of malware generated domains among a regular traffic. There are multiple challenges. Of course, we see most of the traffic is actually a benign one, the valid one, and some parts, some domains are generated by the infected hosts. By the domain generation algorithms, we don't really know if behind a single IP that's communicating with our resolver, if there is a single device, or if it's a house, or if it's a whole large network. So this is also one of the challenges. It could be a whole lot of traffic from a single IP or a few queries during the day. Our ultimate goal at the end is to detect and to point towards the infected clients and to tell, okay, there is an infected client behind this IP, even without actually knowing what botnet is running there, without the prior knowledge of those specific domains. So the first step to do this for us was to try the per domain DGA detection, to actually decide, is this particular domain DGA or not? Of course, it's a bit tricky. So what we tried, we asked a university to hop on board for this research. It was led by gentlemen Carlos Catania, Sebastian Garcia, and Pablo Torres. There are from Czech Technical University in Prague and Universidad de Mendoza from Argentina. And what they brought inside as a data set with our help was over 1 million of clean domains and almost 2 millions of DGA domains from 51 malware, different malware families. You can see the list of the malware families on the right. There is a whole paper available on the URL on the bottom of this slide. I'm not authorized to redistribute the paper, but it's available there, and I encourage you to read it. It's quite interesting. I will just point out a few things out of that paper. The neural network that is actually deciding whether the domain is DGA or not starts with the embedding layer, which creates a whole lot of vectors out of every single domain. So it vectorizes the input to have, I think, 256 vectors for any domain you throw at it. Then there is a single dimension convolution layer that extracts the features out of these vectors. And at the end, there is a multi-layer perceptor network that's doing the final decision: is this a DGA domain or not? So basically, the whole output is a probability, and the result true, false, DGA or normal. So that's quite nice, and this is how it works on the data set with the true positive rate about 97% and false positive rate about 0.7%, which is still quite large. If you imagine the DNS traffic, the false positive rate at this level, it's not really good, not really the only thing you would like to rely on. So we have improved the neural network over the time a bit on top what was the result of this particular research. But at the end, it's as I mentioned, it's really tricky to do the decision on a single domain. I'll explain right away why. Doing the decision just based on the domains led to a real false positives. So we have decided we need something on top of those labels on the individual domains that would evaluate the behavior of the individual hosts and IP addresses communicating with the resolver. I have a few examples here of some of the domains that are actually a valid domains. I've picked the domains from Czech Republic, from CZ domain, and I really like them. The domains here marked in red, they are valid domains of schools, of public institutions that are, of course, they have been marked as DGA by the neural network, because I mean, even me, I would put them in the DGA bucket if I see them for the first time. So our idea was, okay, let's not rely on just the neural network that's labeling the domains, but we need something on top of that, and we have labeled manually sequences of the traffic for 240 DGA sequences over several days, and then clean DNS traffic, almost 250 samples of different clients, different volumes, to have different sequences of DNS traffic, and to be able to feed those to a machine learning algorithm that would be able to decide, okay, this IP address is infected or not. This is one of the point of views that we got from the data set. The cluster on the right, the DGA cluster on the right, are the data sets where there are actually really many queries from the infected hosts. So they are easily distinguishable from the rest. So it's a flood of DGA queries, and it's easy to distinguish them. But the cluster on the left, based on the volume, this is much more tricky. The DGAs here are generating just a few domains per hour or per day, and it's basically overlapping with the regular traffic. Our experience is that 0.01% of the traffic is labeled as a DGA. So it's not a huge amount, and this is the most tricky part to distinguish the clean from the DGA. These are the results from our sequence analysis that's working with the DGA label on long-term traffic on at least several hours or maybe several days. And actually, we got really good results based on that, more than 99% precision based on the time sequences. So we are really confident about pointing towards the infected IP addresses there. How does it look like in the real world? I have a few examples here. This is one of my favorites, actually. This is a really aggressive in terms of number of queries Monero miner, which is sending queries towards these domains. The author of the malware is using these domains, or one of these domains from time to time to update the malware. And the top level domains are is a combination of hosting, OARC, Black Friday tickets, and feedback. And we actually see this malware active for like 2 years. And in many networks, there are still a huge number of infected clients. You can see that during 1 hour, such an infected client is able to see send about 30,000 queries. Even more, we have seen occasions where it was like almost 100,000. There are much more famous like botnets like Necker's botnet. They are a bit more cautious, as you can see here. Every column is 1 hour on the timeline. Necker's uses a large set of different TLDs, and here we are able to see that per hour the traffic includes like 300 different DGA queries. And there are also some other botnets much more cautious. This one is unknown. Our disadvantage is that we cannot really decide whether it's a what type of botnet this is if we don't know, actually, if we don't have the binary, if we cannot link it to a particular algorithm. We just can tell, okay, this is a DGA, it's an infected host, but we are not sure about the particular botnet. So this is, for us, it's an unknown botnet, but still we can tell this is an infected machine here. So as a summary, we are very happy with the DGA detection based on the 2 layers. First, the domain-based labeling, and then taking the whole sequences of the traffic and running them against the clean and infected traffic. It gives very precise outputs. Our challenge, what we would like to solve in the future, is to do the real-time prevention. So directly on the resolver, to be able to mark the infected clients and for them to block and to prevent only the DGA traffic, but keep them online without preventing them the regular DNS resolution. It's quite challenging performance-wise, but it's something that we would like to manage, and we are looking into this deeper. Thank you for your attention. If there are any questions, I'm here to answer them.
Thank you, Robert. We didn't get any questions yet into Zoom, but I will have one question. So this is not really DNS questions, but I'm interested in if you managed to identify some botnet and you were able, can you like reverse the algorithm that is generating these DGA algorithms? Can you then like prevent all queries generated by this malware, or do you still have to rely on solution like this that just like estimates whether the query is DGA or not?
Well, we cannot reverse that without the actual binary. So we can just guess most of the queries that are DGA, but it's not usable to reverse the algorithm behind that.
Okay, thank you. Ali Hussain asked, would it be good to use whois records in real time to predict DGA domains?
Not sure about the answer to this. I mean, most of the domains actually don't exist at the time of the queries. So the whois is a bit tricky. So you can do it for the existing ones, but not for the prediction. I mean, I'm not sure how this would help with the labeling.
Okay, thank you. We have 2 more questions. Sam Cheryl is asking, do you take into account the response code? For example, NX domain responses. For the traffic analysis, botnet polling is often associated with high NX domain counts.
Right, I agree, it is, but we decided not to take this into account for the purposes of botnets that have a low volume of domains and all are actually existing. So we have seen some. One of the botnets I remember is the infected CCleaner, which is like 4 years ago maybe. They actually cycled only 1 or 2 domains per week, and the attacker has already bought all of them, so all of the domains were existing, and this is one of the examples where this would be would be a bad idea to take into account the response.
Okay, thank you. And the last question we got was a duplicate of the first one. So we have one more minute. So if anyone wants to ask a question, you still have a bit of time. And if not, I will just hand this over to Keith because he will have some short announcements. And thank you again, Robert, for your presentation.
Thank you.
Yes, thank you, Jan and Hague, for running this morning's session, and thank you to Shannon and Robert for your talks. Have a few announcements. First of all, I'd just like to thank NS1 as our sponsor of this event today and yesterday. They're doing a survey still where you can potentially be awarded some swag. Also to acknowledge VeriSign as our patron for all our workshops during 2020. A reminder that we very much appreciate getting feedback both on the talks and the event. So you'll see the survey links in the rolling slides. Would appreciate feedback on that. And also, if you're an OARC member and you have not yet registered for the OARC AGM, then there's still time to do so. Again, you should have received a link for that. Just to be clear, that the OARC AGM voting tokens will not be sent out until midnight UTC tonight. That's slightly different from previous announcements on that. We're now going to break for 15 minutes and we will resume at 1500 UTC in 15 minutes. Okay, thank you.
So hello and welcome back. So we have 2 talks remaining, and without any further delays, I will hand over to Brian Summers, who will talk about DNSCrypt, securing traffic from the stub to the resolver. So Brian, if you're ready.
Thank you. I'll just share my screen here. Hopefully you can see that.
We cannot.
Let me try that again. Sorry about that.
Still nothing. Oh, something's coming up. Yes, we can see a screen.
Okay, apparently helps when you click share. Okay, my name is Brian Summers. I work at OpenDNS, or Umbrella, which is a part of Cisco. And I'm going to talk today about DNSCrypt and securing the DNS traffic from the stub to the resolver. I'm going to cover a number of topics, starting with the landscape, what the DNS landscape looks like at the moment, and where the different security zones are, and what's missing in terms of security from for DNS end-to-end. I'll then look into how DNSCrypt actually works and what it looks like in the wild, and then I'll summarize what we've talked about. So the landscape, well, back in the day, I think many of us started connecting to the internet over a 2400 baud modem. We had an environment whereby we either connected to the internet from the office or from home. Our resolver was on our ISP, or maybe if we're a little bit more technically minded, it was in our home or in our office. And the resolver would talk to name servers, and the name servers are out in the wild. The wild got wilder as the internet grew, and DNSSEC was invented, and DNSSEC was invented really to secure that that data between the resolver and the name servers. It takes the name server data and authenticates it and makes sure that it's actually the stuff distributed by the zone owners. But of course, moving towards the modern world, really everything's in the cloud. all of the clients are in the cloud, the resolver is in the cloud, clients move around the place. And the only thing that's really secured in DNS these days is the path between the resolver and the name servers. It's secured in terms of being authenticated. It's not encrypted. It doesn't need to be encrypted because there's very little data leakage from the resolver to the name servers with regard to what the or who the clients actually are. So what's good about having a remote resolver rather than running it all locally on your machine? Well, remote resolvers give you, excuse me, remote resolvers give us good caching. Because there's lots and lots of clients talking to that one resolver, the data that you're looking up in the against the resolver is likely to already be there. High possibility of cache hits. You've got privacy. The authorities learn very little about delegated lookups. They don't really know who's querying the specific name. And with QName minimization, they don't even know what the specific name is. They just know the next zone down from themselves. Generally with enterprise level resolvers, you get low latency. Most of them run on anycast addresses. So if they've got a reasonably good data center spread, then you're likely to get to talk to a local resolver and have low latency. High availability, of course. Most of these big DNS companies will have massive redundancy, and they're able to deal with most denial of service attacks that hit them. And of course, security enhancements. DNSSEC validation is just about everywhere now. Unfortunately, not all zones are DNSSEC signed, but eventually that will come. But also a lot of these resolver services will protect you against things like malware and phishing, and also do content protection and that sort of stuff. So the missing piece, well, the bit between the stub or the client and the resolver is not secured. It's not really secured in any way. So if your resolver is not local, then your traffic is going out in the internet. It's visible by everybody or to everybody. There's no authentication. The DNSSEC AD bit can't be trusted. Well, we can't really trust the data at all because it can be attacked. Most of the queries go out these days with 4K buff sizes, although that's being addressed early next month, in the next couple of days, in fact, by reducing that buff size down to something more reasonable that will avoid fragmentation. But there's really no privacy. Everything's in plain sight, and you really don't know who's watching. So DNSCrypt to the rescue. DNSCrypt is the piece that is there to plug that gap. DNSCrypt is something that lives locally, so it might be a local network service, some server in your local network that takes your plain text DNS traffic and encrypts it before sending it out in the big bad internet. It might be a local process on your machine, so laptops may have local processes that are doing this DNSCrypt, or it might even be built into the Stub library. I don't know of any implementations that do that yet, but that would be a nice thing in the future. DNSCrypt supports UDP and TCP. So it's very DNS-like. It doesn't try to do DNS over TCP or anything weird like that. It allows a 4K UDP buff size, which is a really good thing. If somebody does attack second and subsequent fragments, well, they're just going to spoil the response. They're not going to be able to corrupt or poison the response. DNSCrypt uses ET25519. Which is relatively fast encryption. It's the fastest encryption option that we've got these days. It does mean that the CPU cost is probably between 2 and 3 times what it is at the moment. But well, that's the price we pay. And DNSCrypt has had no known protocol vulnerabilities. It was invented in 2008, and nothing has ever been reported against it. So I'll go into describing exactly what DNSCrypt is. So DNSCrypt kind of has 3 different players. There's the provider, The provider is the entity that owns the resolvers. There might be multiple resolvers. And then there's the resolver itself, and there's the client. And each of these entities has its own key pair. So we're using public key encryption in each of these places. The provider key is used for signing, and the other two keys are used for encryption, the client and the resolver. So the client, the provider creates a provider public key. He stores one half of it privately, and he distributes the public side to the client, and that client side will be used for authentication. So what are the moving pieces? How does this all kind of play out in the real world? So it starts with a very infrequent operation, which is the provider creating itself a provider key. So that might be done once every 10, 15 years. The provider will create this key pair. It will take its private key, put it in a safe somewhere, and not let anybody access it. And then it will take the public side of the key and it will publicize it to as many clients as possible, stick it in its website, etc. Then once every few months, or maybe at most a year, the provider will generate a new resolver key pair. So the resolver key pair will be used for encryption of resolver queries. So the resolver will install the private part on the resolver itself, and it will take the public part and it will insert it into a thing called a DNSCrypt certificate. So DNSCrypt certificate has lots of interesting data in it, but the most interesting thing is the resolver public key. And that resolver public key is signed by the provider's private key, the one that he's stuck in a safe somewhere and doesn't let anybody have access to. So he'll sign that public key and then distribute the public key for or the DNSCrypt certificate with the public key as part of DNS. So it'll be published as a DNS text RR. So then from the client's perspective, the client wants to talk to the resolver. So every hour, and this is based on the DNSCrypt certificate text RR sets TTL. So every hour, the client will refresh that RR set and will choose out of the RR set its favorite key. So its favorite key will usually be the key with the highest version number. Well, certainly the one that's got valid dates, but the one with valid dates and the highest version number. And it will keep that in its back pocket ready for encrypting things. It's only interested in the provider public key, sorry, the resolver public key at this point. So then periodically, once per session, but more often than not once per query, the client will generate a client key pair. So what the client then does, as it talks DNSCrypt to the resolver, it will encrypt every query that it wants to send using the resolver public key. It will add the client public key to that query, and it will send it off to the resolver. The resolver will then decrypt it using its private key, of course, and will go and find what the answer is to that query. And then it will take the response and will encrypt it using the client's public key and send it back to the client. The client, of course, owns the client private key and is able to decrypt that. So we have a situation where the resolver is the only thing able to decrypt the query, and the client is the only thing able to decrypt the response. And all of the gory detail can be found on the DNSCrypt.info website. So what does this look like in real life? So as I said at the start, I worked for OpenDNS. Back in the day in 2011, when we deployed all of this stuff, we were just OpenDNS, and we started encouraging all of our clients to run DNSCrypt as a way of securing that last mile of DNS traffic. So in the last 9 years, we've been pushing hard at this. We've given all sorts of solutions to clients with respect to running DNSCrypt services in their network or on their local machines. And this is what our landscape currently looks like. This is a cross-section of our DNS servers. So in the graph here, you can see the graph goes across 1 week. The light blue at the bottom is our unencrypted queries. The dark blue in the middle is our encrypted queries. And then the yellow at the top is the authoritative data that's being sent upstream, which is all, of course, unencrypted. The people with good eyesight will be able to see there are a few other interesting things on this graph, talking about a process called DNAT. And that's where our resolvers talk to each other when they're having difficulty resolving queries. And that DNAT service also uses DNSCrypt. So DNSCrypt, what does it give us? So in our environment, we basically see that DNSCrypt gives us privacy. Captured traffic can't be interpreted. The traffic between the client and the resolver is all encrypted. If it is captured by anybody, they can't interpret it unless they have the resolver private key. Upstream traffic that goes from the resolver to the main servers is certainly visible, but is not necessarily something that you can do with, because there's no evidence in the packet as to what who the client is that was asking for it. DNSCrypt gives us authentication. The AD bit can be trusted. So when we receive a DNSSEC response from a resolver, the AD bit says if the data is authenticated, AD authenticated data, that can be trusted, and people can act accordingly with respect to DNS policies, etc. And the most important thing is it gives us administrative sanity. So there's no increased packet counts. It's pretty much the same sort of DNS protocol. There are UDP queries being sent out. They all have 4K buffer sizes rather than short buffer sizes to avoid fragmentation. But other than that, if the response is too big, then it's requeried over TCP as you'd expect with normal DNS. All of the DNS traffic, or the DNSCrypt DNS traffic, usually goes over port 443, but certainly in our environment, it can go over port 53 as well. One of the other nice things about DNSCrypt is the traffic is identifiable. Each of the queries and the responses have a magic first 8 bytes in them. So you can actually identify this traffic, even if it is on port 443, and act accordingly in terms of generating graphs and statistics. So next steps. There's a site, dnscrypt.info. I'd encourage everybody to have a look at that. There's an implementations page. Some of those implementations also support DO and DOT, and I'd encourage people to do comparisons. DNSCrypt has a lot to offer as opposed to DO and DOT, which are producing a lot of waves in the community at the moment. There are a number of public services available, not just the OpenDNS resolvers, and tons of different resolver implementations support DNSCrypt. Most, if not all of them, are listed here. And there's a FAQ there as well, and that's definitely worth having a look at. And what are the next steps? Well, really, I would like to work on getting a DNSCrypt RFC together. It's one of the only things that DNSCrypt has never actually managed over the last, 12 years that it's been in existence. So a little early, but that's pretty much all I've got. So I'm open for questions.
Thank you, Brian. So we have received a couple of questions, and I hope we will get some more. But Paul Hoffman is asking, why do you feel that DNS over TLS is something weird like that?
Sorry, the DNS over TLS is?
Something weird like that. I think he refers to the part about DNSCrypt using UDP and TCP. And you mentioned that DNSCrypt is not using something weird like that.
Oh, yeah, so I personally find it a bit strange to take something like DNS, which is one of the protocols that lives at the bottom layer of the protocol stack, and yank it out of there and place it over TCP, which is a much higher layer. Certainly DNS talks over UDP and TCP as we currently see it. But putting everything over TCP with another protocol layer in between seems like the wrong way to go.
Okay, thank you. I hope it answers Paul's question. Brett Carr is asking, obvious question, but do you think DNSCrypt is losing its relevancy with the emergence of DOH and DOT? Do you think it should or can coexist with the new kids on the block?
I would like to think that it is a competitor. I think that the browser owners that have created things like DOH are pushing it way harder than DNSCrypt has ever been pushed. And DNSCrypt has kind of lived in the landscape for the last 12 years, but hasn't really gone anywhere. My understanding is that there were politics around it originally. I don't have a great deal of understanding, most of it's hearsay, but I'd like to kind of turn that around and at least make it a viable candidate. To be honest, I would like to see DOH and DOT lose to DNSCrypt, which is one of the reasons why I'm talking here today. Just on the basis that I do feel that it makes the job of a network operator very difficult. It also completely circumvents the ability to do any DNS level security operations.
Okay, thank you. On that note, I will actually ask a question because you mentioned in your talk that you think that encryption between resolver and authoritative is not needed. And DOT definitely has, or there are at least some efforts to encrypt between resolver and authoritative. So do you think DNSCrypt as it is would be applicable to that, or would it require huge changes?
Yeah, so I guess the issue about the way DNSCrypt works is that the client really needs to know upfront what the provider key is, otherwise it can't trust the resolver key, which is signed by the provider. And so in the scenario between the resolver and the name server, DNSCrypt isn't terribly appropriate. There is another protocol called DNSCurve, which is way more appropriate, where the name of the name server is the key that is used for encryption. And again, that's another EC25519 algorithm. We did support that. There seems to be very few name servers in the wild that actually support it. And DJB, who originally invented the algorithm, seems to not support it anymore. So we've since disabled DNSCurve in our environment. I think as a general rule, communications between the resolver and the name servers, you could argue don't need encryption. Sorry, I'll just stop my timer there. They don't need encryption because as a general rule, the name server doesn't know who the client is that's querying. And with QName minimization, all the name server gets to see is the next level down from a recursive resolver. And so if I'm the com name server, all I'll see is a query for opendns.com. And so I know that that resolver is interested in opendns.com. I have no visibility into where the client is going, or where specifically the client is going, or who the client is. And so it's very useless information that's received to the name server. Encryption, of course, is always better than no encryption. So I don't disagree with the DNSCurve approach if people want to hide that traffic.
Okay, thank you. Ali Hussain, what is the adoption statistics of DNSCrypt? How many resolvers are using this? What about performance in the case as compared to DOT and DOH?
There's actually a whole ton of resolvers. So you can see in this page under many services, there's a URL that lists all of the public servers that do this. There's personally at home, I use some software called DNSCrypt proxy. And DNSCrypt proxy comes with a configuration file stuffed full of all of these public servers. and you can literally go through them and decide which one you want to use. In terms of numbers, there's tens of servers there. So yeah, I'd encourage people to have a look at the list.
Okay. Did you answer the part about performance comparison to DOT or DOH, or do you want to answer that?
Yeah, sure. Sorry, I didn't hear that piece. Yeah, that's the one of the downsides of using encryption. It costs. Even EC25519, which DNSCrypt uses, it costs, I would estimate, between 2 and 3 times the amount of CPU to process a query. So that's the query and response traffic encryption and decryption.
Okay, thank you. Joe Abley is asking or commenting, there's an upswell of activity implementing DOH on application endpoints. In some cases with extensive support in developer frameworks. I haven't noticed as much interest in DNSCrypt. What benefits does DNSCrypt provide in the world where DOH is becoming prevalent? You mentioned that advantages exist, but not what they are.
Well, I guess, I mean, again, looking at the DNSCrypt.info site, there are a bunch of pros and cons for each of the protocols, and it includes DOH and DOT. I think one of the main things that kind of attracts me to DNSCrypt is that it doesn't spoil the administrative landscape, in that we still have a client talking to a resolver and a resolver talking to a set of name servers. So DNSCrypt just owns that client to resolver data path. You can still see UDP traffic and TCP traffic. You can identify that as being DNS traffic, and you can block it and do any administrative things that you want to do with it. The thing I dislike about the other approaches where we send everything over TCP from the client is that it's very difficult to police that client, and the client can connect to anything. It can do its queries over anything, and really, you know, in my kind of view of the world, where a resolver gets an opportunity to provide security to the client, well, that's all gone. The end user, or the zone operator, is the thing that's actually managing security. The TCP kind of approaches, things like adaptive DNS, is even exploring the ability for zone operators to publish things like HTTPS Q-type records that tell the client which dot or DO service to use as a resolver, which is appalling because that completely circumvents any ability to do any security at the network level. But again, we're kind of moving into opinion rather than anything else. I think that the thing I most like about DNSCrypt is the fact that it's just owning that whole in terms of security rather than trying to replace the protocol.
Okay, thank you. Another question is from Brett Carr. Why do you think there has never been any RFCs published for DNSCrypt?
Well, I mean, there's lots of conjecture around that. My understanding is that back in the day, in around 2010, David Ulovich, who owned OpenDNS, had arguments with various members of DNS-OARC and decided to kind of step back from the whole open source community thing. And I'm not really sure how much DNSCrypt was OpenDNS only at the time, but it seemed to me that he kind of basically threw his toys out of the pram and wouldn't play with anybody. And ever since then, no RFC has been written. This is conjecture. This is entirely my own opinion, though. So please don't take that with a pinch of salt, basically.
Okay, thank you. We have, I think, 3 more questions, and some more are coming. So I will just close the mic line because we are running out of time. But the next question is by Paul Muchin, sorry, maybe I'm mispronouncing it. Any vulnerabilities discovered in DNSCrypt so far? For example, an attempt to decipher the encrypted queries using cryptanalysis or side channel attacks.
So I did, there is a paragraph on Wikipedia that claims that there have been no known vulnerabilities in DNSCrypt since its inception in 2008. I haven't heard of any. I don't know of any side channel attacks apart from actually doing some sort of social attack to try to obtain the keys that are necessary. Maybe getting your hands on the private provider private key and generating certificates to usurp the existing ones, or getting into a resolver and stealing its private key. The protocol itself, I don't know of any attacks that have been made against it.
Okay, thank you. Samuel Wheeler is asking, how does a resolver know that it should expect the resolver to speak DNSCrypt, or how do you prevent downgrade attacks?
The resolver code path inside the resolver is remarkably simple to process. So the first 8 bytes of a DNSCrypt query and the first 8 bytes of a DNSCrypt response will have some magic in them. So the queries always start with Q and then 7 other characters, and that's that kind of magic string is based on the DNSCrypt or on the resolver public key. Well, actually on the DNSCrypt certificate. So generally the resolver will be configured to know about specific query magics that it understands. And then it takes the packet and it attempts to decrypt it. And if it manages to decrypt it, it's good. And if it doesn't manage to decrypt it, then it has a look and tries to interpret it as a regular DNS packet. And it's as simple as that. And the client, of course, will then use the response magic to know that it's DNSCrypt and should be behaving in a way that says, well, I sent a query encrypted. It must be encrypted in the response.
Okay, thank you. Brian Dickinson, the data is encrypted directly with the public key of the resolver. There is no perfect forward secrecy, unlike the DNS-OARC protocols. This means future loss of the private key exposes all past captured traffic. Any comment on this risk?
Yeah, it's something that's worried me in the past, and I've developed some utilities to kind of help in the process around that. I think, as a general rule, when encryption is involved, there is a problem with losing your keys or compromising your keys in some way. There's no date per se on the private key or the provider key. So it's similar in a way to DNSCrypt or DNSSEC, I guess, in that if you generate some KSK and then divulge that information to somebody else, they can own your domain. And you're only, well, I guess in the DNSSEC world, you can then contact your registrar and use real words to actually re-usurp or regain control of that domain. I don't have any great answer for this in the DNSCrypt world. If people continue to trust that old provider key and the provider key becomes compromised, there's no clean way of kind of revoking that provider public key. Okay,
thank you. And as we are over the time, I will allow one more question, which is by Eric Zegast. In countries where government monitoring is common or required, do you find that wide area DNSCrypt traffic is routinely blocked?
The only experience I've seen of DNSCrypt being blocked is, I believe, areas in China, or probably all of China, that will block certain ports or try to usurp queries to certain IP numbers. Our marketing people have played with that in terms of listening on different ports so that they can kind of squeeze information by that won't be seen by the country in question. Yeah, I mean, DNSCrypt can talk on whatever port you want to configure it to talk on, and really that's your recourse. I don't really have a better answer than that.
That's fine. Thank you a lot. Thank you for your presentation and also for answering the questions so extensively. And with that, we will go to the next presentation, which is a presentation titled "A New Traffic Capture and Visualization Tool for IMRS" by Jim Hague. So Jim, if you're ready.
Hi.
See the slides. Yeah.
Can you hear me all right? And can you hear this? Can you see the slides?
All is good. I can see the slides and I can hear you.
Excellent. Well, let's get going. One last talk for the day. I'm going to be talking on a new traffic capture and visualization tool for IMRS. My name's Jim Hague. I'm one of the team at Shannon. So without any further ado, let's get underway. Quick overview of what I'm going to be talking about today. First of all, we better get the question of what is IMRS out of the way. IMRS is the ICANN Managed Route Server. For those in the DNS world, this is the route server you will formerly know as LRoute. We're capturing traffic for IMRS and writing it to CDNS files, CDNS being a CBOR-based DNS-specific file format for traffic capture, which pairs queries and responses and indexes common data. We're using this because it generates much smaller files than PCAP, but with most of the same information. And finally, we're visualizing the data by importing it into the ClickHouse online analytic database and displaying in Grafana. And at this point, I would just note that aggregation of data is an important factor here, and we'll be talking more about that later on. A bit of background on the project. We here at Shannon contract for the ICANN DNS engineering team, the team responsible for managing IMRS. Traffic capture is all done by open source code developed through DNSStats. And historically, this function has been performed by using a combination of DSC, so DSC XML files, some PCAP, and a previous Shannon solution, Hedgehog. However, IMRS has now migrated to an end-to-end system, CDNS to ClickHouse to Grafana. I presented CDNS back in, dear oh dear, pre-COVID days at OARConline. The only major update we have on the status of CDNS since that presentation is that the CDNS RFC 8618, was published a month or two after OARConline as in September 2019. Today's talk, I'm going to focus more on the full solution. If you want to know more specifically about CDNS, I suggest you go and look up the talk from OARConline. So, a brief overview of IMRS, because CDNS was designed specifically to target the use case for IMRS. IMRS is roughly 280 hosted servers. I'm describing it here as challenging environments. The servers are grouped into roughly 170, we call them instances, in different locations. And they are ICANN servers, but installed into a donor data center. And at present, the total traffic captured through IMRS is in the order of 17 billion queries every day. Now, a bit more about why I describe the environment as challenging. Well, the big thing here is that all data collection is happening on the same hardware as the name server. That hardware is typically a 1RU server. The job of that server, obviously, is primarily to run the name server. So it's important that data collection, which is a secondary activity, it's important there is a minimal resource conflict. Further, the collected data is stored on the same hardware, again, as the name server. And periodically, uploaded to ICANN servers. And that upload is also constrained to use the same network interface as is being used to serve the DNS traffic. So therefore, it's important that as well as resources on the server, that the size of the uploads is kept to the minimum practical. And if we have a quick overview, quick look at what CDNS does for your file sizes, I'm presenting here tables of file sizes against PCAP. Now, you'll notice that obviously there is a huge difference in size between raw uncompressed CDNS and raw uncompressed PCAP. However, importantly, of course, everybody uses general purpose compression to compress PCAP. And CDNS maintains a size advantage, a notable size advantage, even when compressed quite strongly with the example here is XZ. And the important points here are, first of all, that CDNS after compression is still only 30–40% of the size of the equivalent PCAP. And just as important, the amount of CPU required to do that compression is a lot smaller than required to compress PCAP, because CDNS has already aggregated and commented up a lot of the data that you're compressing. The compressor has less to do. Implementation status for CDNS. If you go to the DNSStats GitHub, you'll find a project Compactor. And Compactor has two components. The eponymously named Compactor program, which is responsible for capturing and compressing traffic to CDNS format, and it will also perform a general purpose compression as well. Traffic capture is either off the network or it can convert PCAP files. And its counterpart Inspector reads CDNS files and can produce two types of output. The primary type I'm going to talk about today is templated text output, which we use to generate files for imports to a database. You supply a text template with field values in it, and the contents of that text template are produced for every single CDNS record. CDNS record is a query and response pair. Inspector can also perform PCAP reconstruction, which is important in this context because Octo requires us to supply them with PCAP files. I've described this as lossy. In this particular case, it's lossy in the sense at the transport level. So for example, we do not precisely recreate TCP sessions. We will create a TCP session when regenerating the PCAP, but it won't necessarily match the original PCAP session. And just for the sake of full disclosure, currently the version of Compactor running on IMRS is a pre-1.0 release that supports a pre-RFC draft CDNS format. However, it's been some months now since we released version 1.0 of Compactor, which writes the RFC format. And the 1.0 version of Inspector reads both the RFC format and previous draft formats. And we will be transitioning IMRS to using the 1.0 in the near future. So, a quick overview of the entire processing chain that I'm talking about today. So we start on each of the individual DNS servers. We have Compactor running, generating CDNS files compressed with XZ, which is built into Compactor. And periodically, these files are uploaded to some ICANN central data servers. Once on those servers, CDNS is supplied to Octo. Octo primarily converts CDNS to PCAP because that's the standard input format for their analysis tools. However, they are starting to explore reading CDNS directly for analysis. What I'm going to be focusing on for the rest of this talk, though, is the is the other processing chain, importing the data into a ClickHouse cluster from where it can be viewed through a Grafana server. So, recapping a little on the compactor deployment. The compactor is constrained to use a single CPU on the DNS server. We have configured it to collect all DNS data that CDNS will support, which is basically all DNS data. For those who've not looked at the RFC or explored the tool, you can configure it to omit unrequired items of DNS data. We write XZ compressed files to local storage. These files are rotated once every 5 minutes. That, of course, is configurable. And the maximum query rates that we can sustain, it's very difficult to quantify because it's largely dependent on the core that you actually have on your server and the compression, the level of compression that you're applying. But typically on the single CPU, we're quite happy handling rates of up to about 80 kilo queries per second. So that's 160 kilo packets per second. Compactor itself is multi-threaded internally and given more resources can go considerably faster. As I've said, periodically files are uploaded to a central collection server. On that collection server, the deployment that we have for processing CDNS is like this. We're using Gearman job server and a suite of small Python programs to handle the data processing. I'll emphasize again that each of the Python programs is small, no more than a couple hundred lines or so. The incoming CDNS files are uploaded to designated name directories, and periodically we scan those directories and add new files to Gearman job queues for processing. We have 3 separate queues. The primary queue converts CDNS to tab-separated value files using the inspector text templating for import into ClickHouse. On the successful conversion, the CDNS file is archived and the TSV is added to a separate queue for import. We maintain a separate queue for TSV imports because TSV import is a lot quicker process than the conversion, and this helps us balance the job processing better. Additionally, we have a third queue which can be optionally used to convert CDNS to anonymized PCAP. You can activate this queue based on a date range and a particular range of servers and so forth. And this is typically used for preparing inputs for DITL. Right, let's turn now to the next stage in the chain, ClickHouse. Now, for those who haven't come across it, ClickHouse is an online analytic database. It's open source. It's focused very much on time series data. It's column oriented, and it uses pretty much standard SQL. And for our purposes, it also scores because there is a Grafana plugin available. So Grafana can access ClickHouse databases for graphing. ClickHouse is used by a variety of other projects in the DNS world, notably Cloudflare, but it's also used by registries in Chile and New Zealand for certain, and I suspect very widely used elsewhere as well. We're using a very simple schema within ClickHouse. We have a single main table holding essentially raw CDNS data, i.e. one query response pair of paired data record per query and response. The important thing here is that once data is entered into the main table, ClickHouse is configured to perform on-insert aggregation of this data. And currently we're aggregating into separate 1 second and 5 minute aggregation tables. And aggregation is a simple process selecting data to be aggregated via a SQL materialized view, but married with specialized storage engines that perform the aggregation. There's quite a lot to read on the subject of ClickHouse aggregation. I've included a link within these slides for those who'd like to learn more. The ClickHouse deployment for IMRS is a 6-server cluster. The import process, as we've said, is handling roughly 17 billion records every day. Disk usage currently is working out at about 1 terabyte per 39 billion records, which is a bit over 2 days of raw data. The management tools that we provide, which again are these small Python programs, provide options to retain configurable amounts of each type of data. So we can have different data retention periods for each type of raw or aggregated data. And finally, the ClickHouse cluster serves multiple Grafana front ends. And as well as Grafana, of course, there is a command line SQL interface which can be used for ad hoc queries for data analysis. To give you some numbers, show you what ClickHouse is capable of when it really gets going. Let's take a sample query of counting, just a simple thing of just counting all the quad A queries received in a week. And you'll see that even working on the raw data, where ClickHouse has to chew through 123 billion records or 4 terabytes of data, it completes that query in 22 seconds, which is none too shabby. Moving to the 1 second aggregation, we see considerable reduction in the number of rows to be processed, which in turn leads to an order of magnitude reduction in the time that it takes the query to process. There is a reduction in the size of data stored. It's less than the reduction you see in the number of rows because of the various, all the different aggregations that we are currently making. And at the moment, we have pretty much a full set of aggregations replicating the DSC data summaries. And if we then move to a 5-minute aggregation, you can see there's further impressive drops in the number of rows to be processed and the query speed, and indeed the data size to be retained, as the larger 5-minute gap allows the aggregation to really crunch down the data. So we have the data in ClickHouse, it's been aggregated, and we can now move on and talk about visualization, for which we're using Grafana. Now, I'm sure you've all seen a Grafana screen. You might not have known it was Grafana, but it's a very well-known web-based visualization platforms. We're using 3 different plot types within Grafana. First and foremost is the time series plots, for which Grafana was designed in the first place. We do have several plots that are bar charts, however. Now, and not time series. And if you've ever tried to do a non-time series bar chart in Grafana, you will know that this is not a straightforward process. The solution we've adopted is to pick up one of the existing standard Grafana plugins, which enables you to make time series plots with the Plotly library, and extend that plugin to provide access to Plotly's bar chart capabilities. We've submitted our modifications to the authors of the Plotly plugin, but to date they have been very, very bad at processing merge requests. So I've included a link direct to our repository. We're also displaying map data using a standard Grafana plugin. Other plugins we're using is obviously the ClickHouse Data Access plugin and an image rendering plugin, which you now need if you want to download PNGs of Grafana graphs. You can go and look now at the live public interface at stats.dns.icam.org, and you'll find it reproduces various DSC-like plots. Currently, this is exposing just 5-minute data, and there is a maximum time duration window as we assess the performance impact on the cluster. ICANN staff internally have access to a different Grafana setup with access to plots based on 1-second aggregation and various other non-public graphs. So I'll conclude with just a quick run through of some screenshots so you can see what you're likely to be up against. Grafana has limited facilities for menus and so forth. So here's the landing page. As you can see, we've just grouped all these plots into various different categories, or dashboards as Grafana calls them. Let's look first at a typical Grafana time series graph. This is queries plotted by different regions. Above the graph, you will see some drop-downs. These drop-downs enable you to restrict the graph to subsets of the total available data. This graph and the next few screenshots are taken off one of the internal systems, so you'll see that the end category is a node. That's an individual server. For the public system, you can only filter as far as instance. And here's a dashboard with several time series plots on it, all very familiar Grafana type plots. I mentioned earlier we can do bar charts, so here's a bar chart. Well, here's 2 bar charts, indeed. I'll mention at this point that geographic client data and client ASN lookup we're doing via inspector template output modifiers, which perform lookups in Max9 GeoLite data. And this obviously is done at TSV generation time on the ICANN servers. Here's a more complex bar chart. I will frankly admit that the data for this has to arrive in a certain predetermined order, and you can find yourself writing some rather interesting SQL, but nonetheless, this is a very good example of what it's possible to achieve with bar charts in this system. A quick look at the geographic location plots. And finally, as I think I mentioned earlier, we have a series of plots for all RSAC information. The system also generates RSAC reports automatically. Again, this is done by some of the Python management tools. And these reports include required images of these graphs, which is the reason that we require the Grafana imaging plugin, but that's the Grafana implementation detail. So, in summary, for us, CDNS, ClickHouse, and Grafana provide a nice flexible package for traffic capture and visualization. Crucially, ClickHouse aggregations give you a great deal of flexibility in choosing trade-offs between storage and performance. And Grafana can reproduce DSC-like graphs, given the right plugins. Finally, the intention is that tools and the schema and so forth will be open sourced. Unfortunately, we're not quite there yet. We probably will not be open sourcing the complete IMRS solution because it's very specific to IMRS, but instead a toolkit allowing you to build a system like this yourself. So thank you very much for your patience listening to the last talk of this OARC. Any questions?
Thank you, Jim. That was a really nice overview of all the tools. We actually have some questions here. Stefan Ubling is asking, does the reconstructed PCAP have the information to calculate the TCP RTT?
No, I don't think it does. The TCP sessions are a complete reconstruction. I'm faking it up inside Inspector. The only timing that we have is the timestamps of each individual query or response, which I don't think is sufficient to regenerate to recover RTT transport level information.
Okay, thank you. Tomáš Křížek asks, you mentioned that you are able to process about 80K QPS with CDNS and XZ compression on a single CPU. Do you have an estimate of the throughput of the CDNS without any compression?
Again, it's difficult to tell. A lot of the overhead, a lot of the problems I have there are, first of all, the overhead of PCAP itself. But off the top of my head, numbers in the region of 100,000 queries per second, I think are possible. But again, you can only at that kind of level apply quite light compression. In fact, varying the XZ compression level, if you're using XZ, makes a considerable difference. And we've also been looking at Z standard compression as better compression than gzip, but with the same CPU overhead as gzip. Z standard isn't currently part of the compactor standard build, but we're looking at it.
Okay, thank you. Martin Volling asks, hi Jim, interesting work. Did you look at other databases besides ClickHouse? And also nice Grafana dashboards. I have noticed you are using FreeGeoIP database from MaxMind. Why not use the paid version? It's not expensive and it supports MaxMind.
It's just simply that the light is adequate for our purposes at the moment. Obviously we can use the paid version. It just so happens that up to now I haven't asked us for it.
Okay, and other database than besides ClickHouse?
Oh yes. When we started this project, we looked at several other databases. We looked at Hadoop and Slack, isn't it? I can't remember. Essentially, what we found was typically import speed into other databases was a problem. Several of the databases we evaluated, we found it very, very difficult to import more than 15, 20,000 queries a second, which was obviously going to be grossly inadequate. And ClickHouse was basically very easy to set up and get running. And to date, we have had no reason to reconsider that decision. We're very pleased with ClickHouse.
Okay, thank you. And the last question is from Brian Dickinson. Are there any other transport level details from TCP that are captured, such as NTU, options, anything else?
No, not at the moment. As I said, the CDNS is focused very much on just capturing DNS level data rather than transport data.
Okay.
So we haven't built that stuff in, basically.
Okay. Thank you, Jim, for your presentation. Thank you for answering the questions. And with that, this session concludes. I would like to thank to Jake, who was doing the timekeeping duties, and I forgot to mention him at the beginning of the session. Please rate the presentations because we really enjoy the feedback, and it helps us next time when we will be evaluating future submissions for the future workshops. And with that, I will hand over to Keith, who has some closing notes for this block. Thank you.
Okay, thank you, Jan, and thank you to all of our speakers this morning. Indeed, we've got to the end of the workshop, so it's time to thank a bunch of people. Once again, I'd like to thank NS1 as being our late-breaking sponsor for this event. Very much appreciated. We're certainly interested in sponsors for our future online events. I'd like to thank VeriSign for being our promoter workshop patron for all of our workshops during 2020, online and offline. All OARC members and supporters whose commitment to OARC has been outstanding during this very strange year. All the grant funding and donors that we've received this year. Our program committee, who have worked really hard under quite challenging. They definitely had to do more than they signed up for a year ago. Again, we're looking for program committee volunteers for 2021. And a special thank you to Shannon, who has served on the program committee for 3 years now and has been chair recently. I'd like to thank all of our speakers. Again, it's on their own time, their own effort. They do this, and for the online workshops, it's actually more of their time because we do things like rehearsals and ask additional information from them. So a big thank you to all of our speakers. Please consider supporting an online OARC event via sponsorship, patronage, or a donation. A reminder to please complete the surveys for the workshop. We appreciate feedback both on the content, which the program committee can use to generate feedback and make sure that the content is matched up, what they rate and what the audience rates is compatible. And also on the logistics of the meeting, we appreciate your input and feedback on the format, particularly with the online environment that we're working in. That's it for me for now. A reminder that OARC 34 will be taking place almost certainly online in February. The call for presentations for that will open shortly. The OARC AGM begins in 1 hour for OARC members and supporters only at 1500 UTC. So thank you all, and if I don't see you at the AGM, see you next time.